All right, so welcome to the end of the week. Happy Friday, everybody. Hopefully you're all surviving the storms. It sure is pretty out there. Can't wait to enjoy it this weekend. So today's plan, of course, I'm going to open it up to you guys for questions on homework and all that, but then we're going to continue talking about finding volumes, specifically volumes by slices, and look at not just ones that are surfaces of revolution, because that's all we've done so far. We'll do a few more of them, but then I want to show you what happens when we can do the same thing even if they're not solids of revolution. So that's my goal today. But before I dive in, homework questions about what we've been talking about, anything I can help with? All right, Chase just threw a couple into the chat box there, 1, 8, and 16 from 2.2. All right, any others? All right, well, if other ones pop up as we're looking, we can definitely do that. So let me just go ahead and share this. We'll pull those up. Okay, so the first question was about number 1 here. So this is a true false, and your true false might be a little bit different, right? When using the method of disks and washers, if you rotate around the x-axis, you integrate with respect to y, and if you rotate around the y-axis, you integrate with respect to x. Okay, so is that true or false? He says, hoping to hear some sort of response. I swear sometimes when I'm doing Zoom, I have the, I'm a huge fan of Pink Floyd and their album The Wall, and there's a line that repeats repeatedly. Is there anybody out there? Sometimes I feel like that when I'm doing this. All right, so let's just think about it. So discs and
true, right?
Okay, so
how you do that.
So we haven't talked about washers yet, but washers is the same idea. It's just instead of a solid disc, you have a ring. But so when we go about the x-axis, that's the horizontal axis, we integrate with respect to y. And if we rotate about the y-axis, we integrate with respect to x. Okay, so let's just think about when we're going about the x-axis, we've got our thing that's getting flipped this direction. And so our circular chunks are such that we don't actually see the circles as we're looking on. We'd see them from the side. And so those circles have thickness, and those thicknesses are going to be in the x direction. And so that means that we need our thicknesses to be dx. So we'd be integrating with respect to x. And then similarly with y. Let me actually draw a picture here. I think this will help a little bit. All right, Chase, I saw your comment about that was actually number 2. I'll come back to that in a second. But since I'm already talking about this one, let me just show you what I mean. So we got our shape, and we're revolving it around the x-axis. So what we're going to see would be something like that. I apologize for the really sloppiness there, but it would look something like that. So when we slice it, the slices are going to be little slices like that, right? So they have a thickness of dx. So when you're going about the x-axis, you definitely want dx's. If you are going about the y-axis, so let's say we had a shape that looked like that, the slices are now going to be in the other orientation, and so they're going to have a thickness of dy, so you integrate with respect to y. So I think my number 1 is actually false, the way that it was worded. But this is how you know. Think of it, the thickness. The thickness of the slices tells you which variable you're integrating with respect to. All right, so I think that's actually then false for mine, but whatever, don't really care. So let's look at number 2. All right, so you wake up one morning and find yourself wearing a toga and scarab ring. Always a logical person, you conclude that you must have become an Egyptian pharaoh. Someone was having fun when they wrote this question. You decided to honor yourself with a pyramid of your own design. You decided you should have a height of 3,470 and a square base with a side of 1710. So to impress your Egyptian subjects, find the volume of the pyramid using integration. I'm going to hold off on this one because we'll actually derive the formula for a pyramid, the volume of a pyramid, using calculus, and then we can come back and answer this question. So I'm going to hold off on that for just 1 second. So then let's go take a look at number 8. All right, so the graph above shows the base of an object. Compute the value of the volume of the object, given that cross sections are squares. Okay. Well, I haven't shown you one that's not cross-sectional, that's circular, right? And this one's not going to have circle cross sections, but this one, it says, has square cross sections. Well, we're still going to be able to do this integral kind of the same way, where we integrate the area, the cross-sectional area, which in this case now, though, is going to be a square. But we're going to have to do this in 2 different pieces. You'll notice that as we're building the squares here, starting at 0, the squares are getting bigger. I don't know if you can visualize the square, but like the distance between these blue lines is one side of the square. So then it would be coming up out of the paper, the same distance to form a square. So those squares are getting bigger until we hit 6. And then from 6 to 8, those squares are all the same size. So we're actually going to break this into 2 pieces. All right, well, let's see what happens when we go to the whiteboard and do this. All right, so thinking about cross-sectional area or just volumes in general, right? The volume is equal to the integral of the cross-sectional area times a thickness. Okay, now that thickness is going to be an infinitesimal thickness, like the tiniest of tiny thicknesses. So that's going to be our, in this case, dx. The cross-sectional area is the area of a square. So it's going to be the side length squared. So let's see if we can figure that out. Now we're, again, going to have to break this into 2. So we'll set up the 2 different integrals. Let me go back to that picture real quick. All right, so the first integral is going to go from 0 to 6. And to get the length of this square, we need to know basically a formula, some sort of function to give us that height. Well, that height is going to be a difference in the equations of those 2 lines. So let's see if we can figure out the equations of these lines. So this one goes through the origin and then goes up to the point 64. So it rises 4 and a run of 6. So it's got a slope of 2/3. So that's y equals 2/3 x. The other one is y equals minus 2/3 x. So what we get for the height is the difference in those 2. All right, so what that's going to look like, let's go back to the whiteboard. We're going to have an integral from 0 to 6 of 2/3 x minus negative 2/3 x squared. Okay, so again, if we look at that picture, it looked like this, right? Home plate. The 2/3 x minus 2/3 x is this height right here. All right, so then the next integral is going to go from 6 to 8. Now we're over in this range. And there, the heights are always the same. That side is length 8, so we'll do 8 squared dx. So the most important thing to get from what we've been talking about so far is this right here, that if you want to get the volume, you integrate the cross-sectional area times the thickness, and the thickness is always going to be a differential depending upon how this is oriented. We usually try to orient it so that we get a thickness of dx, but that's not always possible, so be aware that that can be a dy as well. All right, so is this better for the setup of, I think this was number, I don't even remember anymore, 8, I think. And we're going to play the same trick when we find the volume of a pyramid. All right. So then it looks like we got 16, and then Era's jumped in with 15 as well. Well, let's go take a look at those real quick, and then jump back to the question from 2.1. All right, so 15. So find the volume formed by rotating about the y-axis the region enclosed by 4y, x equals 4y, and y cubed equals x. This is another one I'm going to hold off on for a second because I haven't shown you any washer methods. So after I show you how washer method works, hopefully that will help. And then this one, let's see. So we have a ball of radius 11 has a round hole of radius 9 drilled through its center. So find the volume of the resulting solid. All right, so yeah, we can go ahead and do this one. So let's draw a picture of it first, and then we'll see what we can do here. Actually, give me 1 second. I want to write down these numbers. So radius 9 out of a radius 11. Okay. So here's what we got going on here. We've got a sphere of radius 11. Okay, so it's just a ball. And its radius is equal to 11. And then we're going to drill out a hole. So we're going to come out here and drill out a hole of radius 9. So basically, we're making like a bead maybe or something like that. So you got your sphere and there's just a hole drilled down through the center. All right, now this is still a solid of revolution. If I actually draw what remains, ugh. That was horrible. Hold on a second. Let's try that again. Okay, so here's what remains. We've got hole drilled out, top and bottom. I just have a curve like this. All right, but it is three-dimensional. So we're just looking at this from the side, but it comes out towards us and back towards us. So this is still a solid of revolution. And so the question is, what does this solid look like? Or are we going to set this up? Okay, so I've got it oriented with dy's. So let's go ahead and do dy's. But I want to think about, what does one slice of this look like? So what I'm going to see when I slice this is the outside of the sphere, but then it's got the inside cut out. So let's actually look at that in a little more detail. So this is what our cross section looks like. We call this a washer for obvious reasons, because it looks like a washer, like the hardware piece, right? And so think about trying to find the cross-sectional area of this. Its area is going to be big circle minus little circle, right? If we think about the area of the big circle, we subtract off the area of the little circle, we'll have the area of this washer. Okay, now the little circle is always the same size because that came from drilling the hole through here. And so the little circle is going to have an area of pi times 9 squared. Just good old pi r squared. And the radius of that hole is 9. The bigger circle, we'll call this guy, say, pi times r squared. Let me actually make it a little r. And that radius r is this distance right here. But that radius is changing, right? It starts by being small. If we look down here, the radius is, the outer radius is actually 9. And then it works its way out to 11 and then back to 9. So we need to have a formula that defines that in terms of y. Well, here you go. We just need the equation of this circle. So if I put some axes on here, like how about right down through the center, this is a circle and its equation is going to be x squared plus y squared equals 11 squared. So if I solve this for x, that's the square root of 121 minus y squared. And that x is my little radius. Right? Think about on this picture, the radius of this outside is determined by the x value on this circle. So we'll go ahead and put that in. So this is going to be pi times the square root of 121 minus y squared squared, which of course the square root goes away. And so here is the cross-sectional area, the area of that washer, depending upon what the y is. And so now that we've got that, we can go ahead and set up our integral. So we're going to take that area, so pi times 121 minus y squared. I would definitely do a little bit of simplification on that before I do the integral, but there's our area times the thickness. And the way I've got mine drawn is the thickness is a dy. So now I need y bounds. I need to know what y values am I using, which means what is the y right here at the bottom where the cylinder hits to the top. And to help us find that, I'm actually going to draw this right triangle. Because I know some sizes on that. All right, let me draw it here on the side. So that's that same one right there. So here's what I know. I know that this one is size 9 because that was the radius of the hole that I was drilling through. I also know the long side is 11 because that was the radius of my sphere. And now with that, I can actually figure out what that y coordinate is. So I'm going to have y squared plus 81 equals 121. So y is the square root of 40. Feel free to simplify that, reduce that if you want. I don't really care. All right, well, that happens to be my upper bound because that's as far as we're going to see this shape. Once we reach that y, there is no more sphere. It's all been drilled away. And then from symmetry, I know the lower bound is similarly minus root 40. So some takeaways from this. One, notice that we're still looking at area of the cross section. It's just this time, well, it's a washer instead of a disc. Well, go back to that one where we had cross sections that were squares. Okay, so what? We find the area of that cross section, however it looks. Then we multiply it by its thickness, which is our differential. The last thing is finding the bounds. Now, this one was definitely tricky in terms of finding the bounds, but we were able to do it making use of a little geometry. All right, so is it better for that one? I don't even remember what number we're on, but feeling a little better, hopefully. Okay, so let's go back and look at that one from 2.1. There was a question about something from 2.
Look at it after class. I can with you.
Oh, that's okay. Let's just look at, pop it up real quick. Which number was it again?
10.
All right, and what was your issue?
It's just like that one where you take half of it, and like I think like I followed your process. I've done it like 7 times, and the answer like seems correct if you look at it on a graph, but I don't know if there's like a input error or something.
Okay, well then, since we've already talked about this one, yeah, let's after class, you and I can just bang that out real quick.
Perfect.
Okay, cool. Thanks, Lexi. All right. So I'll tell you what, let's actually keep talking about these solids of revolution and some of the kind of weird things that you can see. But I am going to hop up to the whiteboard because I can draw a little bit better than with the computer. So I will be right back with you guys. All right, so you're starting to see, hopefully, that it's always the same process. It's find that cross-sectional area and add them up. But the challenge is to picture the cross-sectional area. That is definitely something that will cause you some trouble and take some getting used to. But anytime you're doing a solid of revolution, those cross-sections are based on circles. They might have holes, right? Like that one we just saw, but they're always going to be circles. So let's practice some more of those just so you can kind of get the feel a little bit better. So let's do this. Let's look at the area. Let's look at the region that's bounded by y equals x squared and y equals x. Okay, so that's going to be the region that we're looking at. And for the first one, we're going to use this region for a bunch of things. But for the first one, let's find the volume if we rotate about the x-axis. So let's start by drawing the picture. Draw a picture of the region, get a feel for what it looks like, and then we'll start playing with the revolving it. All right, so we all know that y equals x squared looks like a little happy parabola. We all know what y equals x looks like. It's just a line that goes through the origin with slope 1. All right, so here is our region. The region's that little kind of like sliver with a curve right there. All right, now I'm going to erase all the bits of this that are not our region. I don't care about the rest of y equals x and y equals x squared. Okay, but this is our little chunk. All right, so we're going to start by rotating this about the x-axis. So let's spin it around the x-axis. So think about what this is going to look like. Far out here, we're going to get a big circle. It's going to be that line. And then on the inside, there's going to be another little bit of a curve that looks like that. So this is going to look like a cone, but the inside of the cone, instead of being linear, has a little bulge to it. Okay, so think about an ice cream cone that's stealing some volume for you to fill ice cream with that little bulge in the middle. It'd be a really crappy ice cream. All right, so now let's think about what a cross section is going to look like. So if I come on sort of the inside here somewhere, there's going to be a circle that's formed by the line, and then another circle that's formed by the parabola. And so this one, again, is going to have a cross section that's a washer. So it's going to look like this. So mathematicians actually call this the washer method. All right, but it's really the same thing that we were doing before. It's just now there's a hole. All right, so we're going to do exactly what we just did, where we do the subtracting bigger circle, take the bigger circle and subtract the smaller circle. All right, so here's the trick with these. It's the same as before. When we built those circles, we used the functions for our radius. Same thing is going to be the case here. It's just each of the radii is going to be determined by a different function. All right, so let's think about what this area is going to look like. The outer function is the line y equals x. So when I set up this integral, I'm going to have pi times x squared. The inner circle is from the parabola. So I need to take away that area, which is going to be pi times x squared squared. And then all of that's going to be multiplied by a little tiny thickness, and in this case, dx. Right? So your differential always matches the axis. So if you're going around the x-axis, you're doing it dx. If you're going around the y-axis, it's dy. All right, so here's our cross-sectional area times our thickness. The same every time, cross-sectional area times thickness. Okay, but now we need the bounds. So we need to know what x values determine this little shape. It should be pretty clear that the smaller one is 0. Anybody see what the largest bound is, the upper bound is? How far are we going to go out in the x's to get this shape? Good, thanks, Alexi. She just put in the chat box 1. We're going to go out to 1 because that's the intersection of x squared and x. If you take x squared and set it equal to x, then you get 0 and 1 is your solution. All right, so here's going to be the volume of that shape. It's actually not that bad. The washer method is not that bad because you just end up doing the same thing that you did just twice and subtracting the smaller one from the bigger one. All right, so this is going to be the integral from 0 to 1 of pi x squared minus pi x to the 4th. I'm going to go ahead and pull the pi out front. This gives me x cubed over 3 minus x to the 5th over 5, evaluated at 0 and 1. And I think that gives me 2/15 if my brain is working this early. But there you go. So there's the volume of that shape. So getting a washer happens. Sometimes it's not a complete disk. All right, so hopefully this is kind of bringing back a little bit what we did last time. But the key is cross-sectional area times thickness. All right, so now all of a sudden we're using this integral to find volumes. We're adding up a bunch of little volumes. Let's give that little thickness. And an infinite number of those slices gives us the total volume. All right, now I'm going to take that same region and use that same region, but this time let's rotate it about the y-axis. So I'm going to come over here, clean up my picture a little bit. Okay. We're going to take the same thing, but this time let's rotate it around the y-axis. So now if you think about what this shape is going to look like, so somewhere out here, of course, you're going to get a big circle, and the outside of that is going to curve, and then there's going to be the linear slice down in between. So this is going to look like a bowl. So instead of looking like a cone with weird inside, this is going to look like a bowl with weird inside, but the inside is actually conical. All right, so it's like a bowl that had a cone cut out through the middle of it. That would actually be a really hard bowl to have to eat out of, because everything would kind of get caught down at the very bottom. Like you'd never be able to get to the last drop of soup. All right, so now though, if we look at a cross section, the cross sections are going to be in the y direction, but there's still going to be a circle. I mean a washer, right? We got the bigger circle minus the smaller circle. So we're going to want to do exactly the same thing, except now we need to look at this in terms of y. All right, so here's number 2. This is the volume if rotated about the y-axis. So we're going to set it up very much the same. But now there's going to be a dy out here because our slices have dy thickness, which means that the functions that define our radii have to be functions of y. Okay, well, let's set it up same way where we have the outer minus the inner. And we'll start with the inner because that's a little bit easier. That's just the line y equals x, which as a function of y is x equals y. The outer from y equals squared, which if we solve that for x, becomes the square root of y. So this one's going to be the square root of y. So my mic is kind of muted. You can't hear me very well. Now it's better. Okay, well, I think what just happened, my phone tried to, I got a call, and I think it probably affected it a bit. Okay, but we're good. All right, so notice we're doing exactly the same thing. It's just now functions of y. So the last thing, of course, is to get our bounds. But for the y's, the y bounds are the same as the x bounds, because we're going from y equals 0 up to y equal 1. So this is going to be the integral from 0 to 1 of pi times y minus pi y squared dy, which is going to give us pi times y squared over 2 minus y cubed over 3, or I think that's pi over 6. So we get a different volume, but that's because we got a different shape, right? It's not the same shape. So we're getting a different volume. All right, so rotating about x, rotating about y, it's exactly the same idea. You just need to make sure you have your functions of x or your functions of y. Okay, but now what about this? So same region. But this time, that was number 3. Let's rotate it about the axis x equals 2. So I'm not going to use the coordinate axes. Okay, this time I'm going to use another line as an axis. I'm going to use the line x equals 2. All right, let's redraw the picture. It was just kind of getting cluttered there. But our region, again, was between the line and the parabola. But this time, we're going to rotate it about x equals 2. So x equals 2 is going to be the line right here. So when it's x equals, it's a vertical line, right? Y equals is a horizontal line. All right. So we're really doing the same thing. We're just doing it about a different axis. So here's what I suggest. Let's draw some representative cross sections. So like think about this piece right here. As I rotate it about x equals 2, I'm going to get a circle. Like something like that. And then if I think about the same piece but on the outside, I'm going to get a bigger circle. So like there is one of the slices that we're going to see when we rotate about x equals 2. It's still a washer, which means we're going to do the exact same thing of big area minus small area. That's kind of cool. That doesn't change. All right. So let's see if we can get this thing set up. So we're going to want to do the same idea. We're going to do big circle minus small circle. The bounds are still going to be 0 to 1 because the bounds are determined by the region, not what we're rotating about. Right? It's the region itself. So since the region didn't change, it's still going to be 0 to 1. We still need to do outer minus inner. I'm going to write it in words here first. And then once we get those areas, we're going to multiply it by its thickness. And in this case, the thickness is going to be a dy again, right? Because as we slice, it's a little dy thickness. All right, so we got to somehow figure out the inner and outer radii for that washer. So let me draw a like plane view of the washer. So we'll kind of look down on it again. And I'm going to label those radii, little r and big R. Hold on one second here, guys. The sun came out. It's giving us some nasty glare on the board. All right, so we need to figure out outer radius and inner radius. So I'm going to call those big R and little r, just to help us differentiate between them. Okay, so big R and little r. So let's think about where those are on our picture. So on our picture, here's a little r. It's going to be the distance from the axis that we're spinning around, which is x equals 2, and the closer of the two functions, which in this case is going to be y squared. Okay, so that's little r. So little r is going to change though, right? The biggest it's going to be is 2, one around here, and the smallest it's going to be is 1. But we need to be able to describe how big that is. And we're going to want to use that function. All right, well, how about this? What is this distance that I'm putting here in orange? Can anybody tell me how long that's going to be? If I give you a y, can you tell me how far out I go?
Would it be r plus y?
So you say 1 plus y?
Or I said r plus y.
R plus y. All right, well, if you think about the r plus, wait, add it. I think maybe where you're going with this.
R plus x. Wrong variable, sorry.
We know that the r plus x is going to equal 2.
Mm-hmm.
Right? Because that orange is a distance of x, and x plus r is going to bring us out to 2. So little r is going to be 2 minus x.
Yeah.
Okay, yeah, you're totally on the right track. But think about what I need. I need this in terms of y. So I need to replace that x. Okay, well, in this case, that x, like we saw before, is actually the square root of y. Because we're at y equals x squared. So that radius, little r, is going to be 2 minus the square root of y. So when y is equal to 0, it's a radius of 1. When y is equal to 1 or 2, when y is equal to 1, it gives us a radius of 1. It kind of matches, but that's how that one's changing. So in terms of our inner area, we're going to have 2 minus root y squared. All right, well, now we got to figure out what big R is. So let me go to another part of this graph and let's draw a big R. All right, so I'm going to erase our little circle here. We already know what our washers are, but now here's another picture where this is big R. And we can do kind of the same thing. Or if we think about that distance, I'll leave it orange. That's also x. So what we know is that big R plus x is also going to equal 2. So big R is also going to be 2 minus x. But now the x is given differently. That x value is determined by the line. And that line was y equals x. Well, I don't want it as an x. I want it as a y. But since x equals y, I can just make that 2 minus y. All right, so if we rotate about a different axis, other than the coordinate axes, the function itself is not going to give us the radius. It still matters with the radius, right? You can see that those functions are still in here, but we have to adjust to where our new axis happens to be. So your radii is going to depend on both where that axis is and what the functions are, not just the function. But again, we're getting circles. In this case, another washer. All right, so solids of revolution. We can always do this. Always do slices, and those slices are always going to either be discs, if they're solid, or washers. Either way, you're just finding areas of circles, pi r squared. All right, so the challenge here for sure is seeing the radii. If you're someone who visualizes well and see the geometry, this is going to be a lot easier. For those of you that's a challenge, this will be more difficult. But there are definitely patterns. like the fact that the 2's showed up in here, and it's 2 minus the radius, or minus the function. There are definitely patterns. There are too many cases for me to actually want to go through and develop them all. But if you're a non-visual person, but you're good at like memorizing all the different scenarios, you can definitely create a chart of what the radii look at like, depending upon where your axis is. All right, but we don't always have circular cross sections, right? Like in that example where we had the square cross sections and all that. It doesn't change anything, though. It doesn't change anything when we do our integral, because we're still going to integrate area times thickness. It's just now our area isn't a circle, so we're not using pi r squared. So I want to do this. Let's actually develop the formula for volume of a pyramid. All right, so we're going to see if we can actually develop that formula. I don't know if anybody knows it.
Is it 1/3 base times height?
Okay, good. Yeah, it's 1/3 base times height. If you look at a pyramid, and this is going to be a square pyramid. Okay, so it's got a square on the bottom. So this is the good old pyramids we see in Egypt kind of thing, right? It turns out that the formula for the volume of this, if we call these sides, let's say B and B, and then we were to look at this right here, call that H, the volume is 1/3 B squared H. All right, I think Susanna said it was 1/3 base times height. You think about the area of the base is that B squared. Okay, so this is just a formula that you were probably told at some point in geometry. You smiled, nodded, and said, okay, sure, that's the volume. Well, we can now prove this. We can use calculus to show that the volume must be 1/3 B squared H. So let me show you. So what we're going to do is think about slicing it. Now, the easiest way to slice this is if we were to slice like parallel to the ground in this picture, so that one of the slices would be right here. It's going to be a square. It's going to be a square slice, and the size of that slice is going to change as we move along. All right, now to help us out, I'm going to turn this pyramid over so that the top of the pyramid is actually at the origin. And then it's going to come out like this. Okay, so I'm just going to rotate it. This is going to make the math a little bit easier. It's going to be easier for us to set this thing up. All right, so some things we know. We know that this distance was h. So that means that this right here is x equals h. So the x's are going to go from 0 to h. I also know that this height right here is b. So that means that this is b over 2. It's half of the base. All right. So that, I just translated all our information over here. But let's see if we can find our volume now. So the volume is going to require us to figure out the cross-sectional area. So the cross-sectional area is going to be a square with this length. All right, so if we can figure out this length, then the area, let me call that L, is going to be that length squared. Okay, so our goal is going to be figure out what that length is. Well, to figure out that length, it's probably going to be useful if we know an equation for this side. So let's see if we can find an equation for that line. So think about what you need for a line. You need a slope and you need the y-intercept. Well, the y-intercept we know is 0, so that's going to be 0. But we need to figure out its slope. Well, the slope of this line, if we think about rise over run, we're going to go up b over 2, and then we're going to divide by how far over we go, which was h. So this is b over 2h. So the equation of that line is y equals b over 2h times x. Just slope times x. So my side then is 2 of those, right? Because y is just the distance from the axis up to that. So I got to double it to get my length, which is just bx over h, which then means that my area is bx over h quantity squared, or b squared x squared over h squared. So there's the area of the square cross section. It depends where we are, right? How far along have we gone? When x is small, this area is small. Got small squares over here. When x gets bigger, I get bigger squares. But now that I've got that, I'm ready to get my volume. Because remember, the volume is the integral of our cross-sectional area times thickness. And the way that I've got it set up, my thickness is going to be a dx. So the last thing is to put on our bounds. And for this one, the x's go from 0 out to h. So this integral right here is going to calculate the volume of that pyramid. All right, well, the b and h are constants. So let me pull those out. So we're integrating x squared. So not only were we able to set up the integral, it's actually a really easy integral to do. We love integrating x squared. So this is going to be b squared over h squared times x cubed over 3 evaluated at 0 and h. Well, that's b squared over h squared times h cubed over 3. Cancel some h's. And we get that infamous formula, volume equals 1/3 b squared h. All right, I don't know if you appreciate this or not. I love this. I love being able to now show where these formulas came from. Because I don't know about you, but this was not obvious. When I was first taught the volume of a pyramid is 1/3 b squared h, where the hell did that 1/3 come from? It's not intuitive at all. You know, even when you look at it geometrically. But as soon as I learned this, I was like, oh, totally, it has to be 1/3. You can do the same thing to figure out like the volume of a sphere, right? You know that formula, the volume of a sphere is 4/3 pi r cubed. If you've ever wondered, where does that come from? This. The cross sections are circles, right? It's a solid of revolution. Well, you could do exactly the same kind of thing. Look at the cross sections, and you'll see why the volume of the sphere is 4/3 pi r cubed. Right? I think we saw why the cone was 1/3 pi r squared h. It comes from the kind of the same deal. But this is powerful. Now you're starting to see where this stuff comes from. And I appreciate what you just put in the chat there, Rigney. I too am a huge fan of knowing why things are. Because people say lots of stuff. Right? I can tell you anything. Doesn't mean that it's true. Right? And in the world we live in, you guys all know what I'm talking about. Like, there's a ton of stuff out there that's complete and utter garbage that people are just spouting off. Right? I like to have a little bit of evidence. I like to have something backing up the statements. And in math, man, oh, the evidence is huge, right? It's not just suggested this is the volume. No, it must be the volume because we know this is how we do it. Anyway, so hopefully you at least find this kind of interesting, but now you know exactly why the volume of a pyramid is 1/3 base times height. So if you go back to that question from the homework, I think it was question maybe number 2 that Chase asked about with the you wake up in a toga and with a scarab or whatever nonsense. That's exactly this, except they give you a specific base and a height. So your equation for your line isn't going to have B's and H's in here. It's going to have a number, right? You plug in your base, you plug in your heights. You'll get your line is, let's say, y equals 27x. Okay, well, once you've got that line, you can go through the process and get the same thing. But a real mathematician would recognize I just did every single pyramid. Every single pyramid's integral is going to be exactly the same. So we get this formula, right? And again, that's how mathematicians like to think. Do all the work one time. You do the work once, you never have to do it again. You can jump straight to this equation. All right, looks like we're out of time. In fact, I'm a little bit over and I apologize. But just to let you know kind of where we are. We have an exam next week. Just want to remind you about that. It's going to go through up to and including this section. Okay, I'm going to end it at this section. So just so you know, you can start planning for your exam. So it's going to be chapter 1 and sections 2.1 and 2.2. Okay, we'll talk about this next week as well, but I just want to get it out there. So if you want to start studying, get ready. That exam is going to happen on Friday. Monday, there are homeworks that are due. 2.3 was due on Monday, but I have now extended that because we haven't talked about it. So the last homework assignment that's going to be due on Monday is 2.2. So make sure you work on that stuff. All right. But other than that, have an awesome weekend. Enjoy getting out there and playing in all this fresh snow if you're so inclined, or wherever you happen to be. Go out and have some fun. All right. So I will see everybody on Monday. Have a great weekend.
Thank you, Bruce.
Peace out. Have a good weekend.